Hello, everyone, and thank you for joining another live webinar session brought to you by Tech Media. My name is Jason Montgomery, and I'm going to be the moderator for this session. Today's session is brought to us by Vishay Technology, and the name of the session is 400 volt, 100 amp bidirectional eFuse for load monitoring and protection. Let me tell you a little bit about our presenter, and then we'll go right into the presentation here. Our presenter today is Scott Blackburn, who's the manager of automotive field applications. He received his bachelor's and master's degrees in electrical engineering with a power electronics focus from the University of Toledo in Ohio, later receiving an MBA from Bowling Green State University. He's been with Vishay for nearly 15 years and is responsible for field application engineering and business development in the Americas, supporting all of the company's automotive products. And again, I want to thank everyone for joining us here for this session. And as a reminder for all of these live sessions, we do have a Q&A that will come after the presentation. So for everyone here that's in the audience, please make sure to submit the questions that you have in mind, and I'll be happy to go over those questions with Scott once his presentation is concluded. And with that, I'm going to hand it off to Scott.
Good morning, good afternoon, good evening, everyone. My name is Scott Blackburn, and I manage automotive field applications engineering and business development for Vishay in the Americas. Today I'm going to talk about a unique reference design that's been developed by Vishay that can be used in any 400 volt load applications up to 100 amps. With the steady increase in high-voltage e-mobility applications, semiconductor-based resettable fuses are quickly replacing mechanical relays and contactors and traditional non-resettable fuses. As you can see in this typical block diagram, there is usually a power distribution unit located between the high-voltage battery and the various high-current loads such as electric power steering, the HVAC system, and others. In a conventional implementation, the power distribution unit would house all of the high-power contactors and standard non-resettable fuses. Now, as electric vehicle architectures are progressing and improving, those contactors and fuses are being replaced by solid-state hardware. The electronic fuse, or eFuse concept as it's commonly known, is an innovative new trend for protecting both the user and the hardware in high voltage and high power applications. In a new reference design by Vishay, an eFuse has been designed to handle continuous power up to 40 kilowatts. It can operate at full power with less than 30 watts of total losses and no active cooling, and also features a pre-charge function, continuous current monitoring, and overcurrent protection, with complete shutdown in less than 2.5 microseconds. Okay, just a little bit more detail on the contactors I mentioned in the previous slide. As I said, these are conventional electromechanical devices that are basically a high-power version of standard low-voltage relays. They typically do not provide overcurrent protection, so standard non-resettable fuses are used in conjunction with the contactors to disconnect the load from the battery in the event of a fault or short circuit. Since these contactors are mechanical devices, they have a limited lifetime compared to a solid-state solution, and they also tend to be large and expensive. However, the biggest drawback to using contactors and fuses is that it's not possible to easily or quickly reset them once the overload or fault condition at the load has been cleared, which can lead to an inoperable vehicle. Therefore, in order to maintain the life expectancy, system flexibility, and safety requirements of the vehicle, we've developed a unique electronic switch and resettable fuse, or eFuse, that can be used in any high-power application up to 400 volts and 100 amps, which I'll spend the rest of this presentation discussing in more detail. The Vishay eFuse has been designed to safely connect and disconnect a high-voltage power source, typically a high-energy battery pack, to any type of vehicle load using power MOSFETs as the primary switches. If the current exceeds a predetermined limit, the load is quickly disconnected from the battery pack to protect both the battery pack and the user. The eFuse can also detect excessive load capacitance or a short circuit during power-up and immediately shut down. The eFuse is constructed using standard double-sided 4-layer FR4, which utilizes 70 micrometer thick copper for each layer. The overall dimensions of the PCB are 150 millimeter by 90 millimeter, with some extension of the connectors beyond the edges. Most of the high voltage circuitry is located on the top side of the PCB, along with the connectors, control buttons, status LEDs, and multiple test points. The low voltage circuitry is located on the bottom side of the PCB, along with some of the high voltage control circuitry. In addition, the eFuse can be controlled remotely using a web browser that will be described in more detail later in the presentation. The heat generated by the power MOSFETs is transferred to the back side of the PCB using thermal vias to a solid layer of copper, and then to a heat sink, which is electrically isolated from the high voltage circuitry. To give you an idea of the basic architecture, this schematic shows a simplified version of the power stage. The high voltage battery input is on the left, and the output voltage to the load is on the right. I'll go through this in much more detail during the rest of the presentation. To give you an idea of the layout, you can see the top and bottom side component footprints, and I'll be using these layouts to point out some more details as we go through the rest of the presentation. The main high voltage power stage components are located on the left-hand side of the top of the board. The low voltage control circuitry is located on the right-hand side of the bottom of the board, along with the high voltage control circuitry near the center of the board. Also note the isolation barrier, highlighted in yellow, which separates the high voltage from the low voltage for safety purposes. I will also discuss this in more detail later in the presentation. The eFuse must be able to switch currents that are flowing in either direction. Therefore, two sets of 6 parallel connected MOSFETs, labeled TR1 to 6 and TR7 to 12 in the schematic, are connected in a back-to-back configuration to prevent current from flowing back through the MOSFET body diodes to the battery when the load is deactivated. In this case, silicon carbide MOSFETs were used for the main switches, since they're more efficient, can conduct heat away more easily, support higher current densities, and perform more reliably at higher temperatures compared to standard silicon MOSFETs. To prevent high voltage transients during switching, the MOSFETs are bypassed with a double RC snubber, labeled R1 and C1, and R2 and C2 in the schematic. In this case, Vishay VJ open mode design ceramic capacitors and Vishay MMB 0207 power resistors were used for the snubber. Using this switch arrangement, the total losses can be limited to under 30 watts at 100 amp continuous operation, which is pretty impressive considering a nearly 40 kilowatt output. Taking a look at the layout, you can see the two sets of 6 parallel connected MOSFETs on the top of the board, along with the dual RC snubber at the bottom. They're all situated as close together as possible in a symmetrical arrangement to minimize any stray inductance or capacitance, and also to make sure the current is shared equally between them by having them all stay at approximately the same junction temperature. A little more detail on driving the parallel power MOSFETs that I just discussed. Sometimes small details like choosing a gate resistor get overlooked, but in this design it's fairly important due to the several amps of peak current that's required to turn on a total of 12 MOSFETs at the same time. Using a typical thick film resistor might be a first thought when picking the gate resistor, since the average power is pretty low. However, it's the pulse capability that's the key consideration in this type of application. Most standard thick film resistors do not handle large pulses of current very well, and will eventually degrade and even fail. Therefore, another technology should be considered for high pulse current applications. In this design, a thin film technology was selected, specifically the MMU series from Vishay. It's available in 3 sizes in the cylindrical MELF package, and in this design an 0102 package was used. It has a very high pulse capability, which is important in this application as I mentioned a few minutes ago, due to the amount of extra surface area it has compared to a standard flat SMD package with the same footprint, as you can see in the diagram. It's also a very stable technology, which means that the resistance value will not drift very much over time and temperature. And for reference, it's available in a wide range of values. In order to protect the battery, the vehicle wiring, and greater damage to the load in case of a short circuit, the load current is continuously monitored using a shunt resistor, labeled R5 in the schematic, that's located between the two sets of main MOSFETs. When a predefined overload current is exceeded for over 300 microseconds, the controller can quickly disconnect the battery from the load with minimal time delay due to our hardware comparator circuit that was used in this design, which I'll talk about in more detail in a few minutes. There's also another non-adjustable current limit that has been implemented directly in the hardware. In the event of a direct short circuit, which results in an extremely fast pulse of high current, the load will be quickly disconnected to protect the battery. When the current exceeds this 350 amp limit, a comparator is tripped within 2 microseconds, and then the MOSFET gates are discharged within 0.5 microseconds for a very fast detection and complete shutdown within 2.5 microseconds. Taking a look at the layout again, you can see the current shunt in relation to the two sets of power MOSFETs. Again, this symmetrical layout is used to minimize any stray inductance or capacitance and provide the best possible performance. In this design, a Vishay WSLP 3921 was selected with a 100 microohm value to minimize power dissipation and provide the best signal-to-noise ratio for the feedback circuit. A differential voltage measurement is taken across the current shunt and then fed into a current sense amplifier, which I'll discuss in more detail shortly. However, I wanted to take a quick sidebar and explain why a current shunt technology was selected for this design. In most high current applications like this one, the current needs to be monitored for control purposes or overload protection. There are two methods that are commonly used for this purpose: a resistive current shunt and a Hall effect sensor. A Hall effect sensor is relatively simple to implement as a turnkey solution compared to a current shunt, which requires some additional feedback circuitry, but it can suffer from the following disadvantages: low linearity over a wide current range, offset error due to wide variations in the temperature. There can also be excessive measurement latency and bandwidth limitations depending on the switching frequencies being used. And a Hall effect sensor will also saturate when its current range is exceeded and will be unable to provide an accurate measurement. In addition, a Hall effect sensor requires a separate power supply for operation. And finally, the overall system cost tends to be somewhat higher with all things considered. One more point: customization of a Hall effect sensor is usually not cost-effective or even possible, whereas a Vishay current shunt could be configured to meet the mechanical constraints of the system, either in one of the many standard packages from 0603 to 5931, or a customized version of the larger 8518 shunt. As mentioned before, the WSLP 3921 was selected in this design. The Vishay power metal strip design features an all-metal welded construction, so in addition to the benefits described in the previous slide, it can also handle very high pulse currents for up to 5 seconds that can occur during overcurrent or short circuit conditions. The WSLP 3921 offers the lowest possible resistance values of the surface mount power metal strip series, down to 100 microohms, and it also offers the highest power rating of up to 9 watts in this package size. The WSLP 5931 can also be used if even higher power ratings are required, up to 15 watts. The raised element package, as you can see highlighted in the red box, also lowers the resulting hotspot and keeps it away from the printed circuit board, which may not be able to handle the same operating temperature. If needed, the WSLT 3921 series extends the temperature range up to 275 degrees C for high ambient temperature conditions, such as underhood applications, or for added headroom with the necessary derating curve. Now, back to how the differential voltage measured across the current shunt is processed. Here's a detailed view of the current sense amplifier that was used to take the very small voltage in millivolts and amplify it to a voltage level that can be used for control and protection. In this case, that amplified voltage is fed into both the microprocessor for current monitoring and also into the comparator circuits, which I'll get to shortly, used for the overcurrent detection and short circuit shutdown. Before the amplified current sense voltage signal can be fed into the microprocessor and comparator circuits, it must first be run through another op-amp, labeled U13 in the schematic, to correct for any input offset voltage. Then it must pass from the high voltage side to the low voltage side across the isolation barrier, which necessitates some further considerations and components. In this case, a linear optocoupler, labeled OC1 in the schematic, was used for this purpose, which I'll describe in more detail shortly. However, first, I need to explain a little bit more about the isolation barrier that's required in any high voltage application for safety purposes, in terms of protecting the user from potentially getting in contact with high voltage as a result of a failure within the hardware. The low voltage circuitry ground reference, the vehicle chassis in most cases, cannot be used for the high voltage circuitry ground reference in order to prevent high voltage from getting to the vehicle chassis and in turn to any passengers. Therefore, galvanic isolation is required in these types of applications. In other words, the low voltage circuitry must be completely separate from the high voltage circuitry in terms of power supplies, grounds, and signals. If power or signals need to pass from one side to the other through the isolation barrier, special methods or components must be used to maintain the galvanic isolation. In this design, the components on the high voltage side must receive voltage from the low voltage side, and they must be galvanically isolated from each other for safety purposes, as just discussed. Therefore, two AC voltages of 0 to 12 volts are created on the control side using a 200 kHz switching frequency. This energy is transferred capacitively via two capacitors across the isolation barrier to the high voltage side, where it is rectified back to the original supply voltage level as shown in the top part of the schematic. The red line indicates the isolation barrier. Once again, Vishay VJ open mode design ceramic capacitors were used for this purpose, as they have optimal properties for this type of application in terms of high voltage and AC ripple capability. For transmitting the voltage and current measurements between the high voltage and low voltage side, the galvanic isolation must also be maintained. In this design, a Vishay high-speed linear optocoupler was selected for this function and is shown in the bottom part of the schematic for one of the voltage measurements, which I'll highlight later. The Vishay VOA 300 linear optocoupler is a good choice for this design since it offers 0.01% linearity and high gain stability over temperature to maintain the precise voltage measurement as it passes across the isolation barrier. The 1.4 MHz bandwidth and less than 2 microsecond response time are needed to provide high-speed response for the current measurement, especially in a short circuit condition. This optocoupler is also rated at 5300 volts RMS for the isolation voltage in conjunction with either the DIP8 or SMD version package, and it has a single-ended output. Okay, finally jumping back to the rest of the details on the current sense feedback. I mentioned a comparator circuit that was used to detect an overcurrent situation. Once the amplified current sense voltage, highlighted in the red box in the top left corner of the schematic, has passed through the linear optocoupler across the isolation barrier, It is continuously compared to a preset reference voltage that corresponds to an overcurrent event. When this level is exceeded, the comparator trips and an overcurrent signal is sent to a microprocessor interrupt, and the main load switches are immediately opened. In order to make sure the reference voltages and trip points don't drift over temperature and time in the field, a matched pair of resistors, as shown in the other red boxes, should be used on any op-amp circuits. Even if thick film resistors with exactly the same initial value were used, the resistance values will drift significantly when they're initially soldered, with temperature and with time in the field, and even possibly in opposite directions. Therefore, a thin film technology should be selected for this type of circuit application. In this design, a Vishay ACAS precision thin film resistor array was selected. The array is available in either a 2x or 4x configuration, and resistances of any value can be freely selected for each of the resistors up to a 1:100 ratio. Due to the thin film technology and the fact that the individual resistance elements are manufactured on a common substrate, you can get very impressive individual tolerances down to 0.1% and matching tolerances down to 0.05%. In terms of the relative temperature coefficient, you can get down to 5 ppm tracking between the resistors. Another feature of this design prevents a common issue that occurs when first connecting the battery to the load during vehicle startup. That is, the potential inrush current due to any uncharged capacitor banks in the load. If this resulting high peak current is allowed to occur, downstream components could be damaged and the battery lifetime could be reduced. Therefore, a pre-charge circuit must be used to limit the inrush current to an acceptable level. In this case, a Vishay high voltage MOSFET, labeled TR13 in the schematic, and a Vishay power resistor, labeled R4 in the schematic, were used to implement a two-stage pre-charge function. In the first stage, the MOSFET is energized, and after 25 milliseconds, the output voltage is measured to see if it is greater than 10% of the input voltage. If the output voltage remains close to 0 volts, a short circuit condition exists in the load, the pre-charge stage is terminated, and an error is displayed. If the first stage is successful, the pre-charge will continue. During the second stage, the output voltage is measured after 250 milliseconds to see if it has risen to at least 85% of the input voltage. If the total capacitance of the load is excessive, the output voltage will not rise sufficiently, the pre-charge stage is terminated, and an error is displayed. If both the pre-charge stages have been successfully completed, then the MOSFET is switched off and the 12 main power MOSFETs are switched on, as described before, to energize the load. As you can see from the layout, the main pre-charge components are located on the top side of the board near the 12 main power switches. The power resistor used for the pre-charge circuit in this design was a Vishay D2T035 resistor. It's a thick film technology in a D² pack surface mount package and is designed for very high pulse load applications. The nominal power rating is 35 watts at a 25°C case temperature, but must be derated for higher operating temperatures. However, in this design, since the pre-charge circuit is basically a pulsed event, care must be taken to make sure the peak power rating of the resistor is not exceeded during that time. In this case, a 3.3 K value was selected for the 250 millisecond pulse, which is safely within the capabilities of the power curve shown here and in the datasheet when extrapolated out to the required time. Since the gate drive signal from the microprocessor to the pre-charge MOSFET must cross the isolation barrier, we must once again select some type of component that will maintain the galvanic isolation for safety purposes. Since this is just an enable signal that switches at a relatively low frequency, we have used an optocoupler with a phototransistor output. Once again, the red line indicates the isolation barrier. The Vishay VOM A617A optocoupler is a good choice for this function as it provides a high current transfer ratio with a low input current and a high collector emitter voltage for switching the pre-charged power MOSFET, as well as low coupling capacitance. This optocoupler is also rated at 3750 volts RMS for the isolation voltage in conjunction with the SOP-4 mini flat package. Just a quick comment on voltage sensing, since it's required in the pre-charge circuit to monitor the output voltage, and also in several other places in the design, the input voltage for example. In this case, the high voltage is first scaled down using an integrated voltage divider by a factor of 200 to 1, and then transmitted with minimal delay to the control side using the Vishay VOA 300 high-speed optocoupler that was discussed previously. Once again, in order to make sure the voltage dividers used to make these measurements don't drift over temperature and time in the field, a matched pair of resistors should be used for any critical voltage measurements that are used for control or protection. Although a CDMV2512 resistor divider was used in this design, which is not an auto-grade component, we would recommend using our CDMA2512, which is the auto-grade version that will be released very soon. It has a maximum working voltage of 1415 volts and is offered in a wide range of values and ratios with tolerances down to 0.5% and typical TCR tracking of 50 ppm. This divider comes in a 2512 package and can be ordered with either a 3-sided wraparound or single flip chip termination. In order to protect all of the downstream components in any electronics module from high voltage or high energy transients that can be induced on either the high voltage bus or the load, some type of transient voltage suppressor is typically utilized in most designs. This type of device will absorb the energy contained within the unwanted transient pulse and clamp the resulting waveform to a level which is no longer harmful to the remainder of the components in the module. In this design, a transient voltage suppressor with a working voltage of 480 volts was used on both the input and output, labeled D1 and D3 in the schematic, to protect the eFuse circuitry from transients injected by either the high voltage battery or the load. The location of the transient voltage suppressors is critical when considering the layout. In this design, since we're trying to protect all of the components on this circuit board from transients that may be injected from either the high voltage battery or the load, the devices need to be located as close as possible to the source of the transient to minimize any stray inductance or capacitance which may slow down the response of the TVS. Therefore, one has been placed directly between the input terminal and the power ground connection, and the other between the output terminal and the power ground connection. In this design, a Vishay 1.5 SMC series transient voltage suppressor was selected, which features a glass passivated chip junction to minimize reverse leakage. It's available in working voltages up to 540 volts and can be ordered in either a unidirectional or bidirectional configuration. This series also has a very high pulse load capability, up to 1500 watts for a standard 10/1000 microsecond pulse, all in an SMC package. In regard to the power supplies required for the operation of the eFuse, it must be connected to an external voltage source between 10 and 16 volts and requires approximately 60 milliamps of current. This external supply is used to provide power for all of the low voltage control circuitry through a 5-volt regulated power supply, which is shown here in the schematic. To minimize the space required, an integrated synchronous buck converter was used, which I'll describe in more detail in the next couple of slides. The external power supply is also used to provide power to the high voltage circuitry, which I described earlier when discussing the isolation barrier. Looking at the layout, you can see that only a very small section of the printed circuit board on the bottom side was required for the complete power supply. Here's some more details on the synchronous DC to DC converter, which is a Vishay Microbuck series product. The actual part used in this design is from a commercial family, but we're in the process of releasing an automotive grade version as shown here. It's an integrated multi-chip design that incorporates the control IC and both of the power MOSFETs in a 5x5mm package. The only other components required are the storage inductor, an output capacitor, and some small resistors and capacitors to set some of the control parameters. It has a very wide input range from 4.5 volts to 65 volts, so it can be used in just about any automotive application, either on the 12-volt bus or the 48-volt bus. The output voltage is adjustable to any value down to 0.8 volts, and there will be two output current options available, 6 amps and 10 amps. It's also a highly configurable system, with the switching frequency being adjustable anywhere from 100 kHz to 2 MHz, and the soft start and current limit functions adjustable as well. Release of these new automotive grade products are planned for later in Q4 this year. I also wanted to spend a few minutes on the details of the storage inductor that was used for the power supply. In this case, a Vishay IHLP 2525 22 microhenry inductor was selected based on the criteria described in the Microbuck datasheet. The Vishay IHLP family of inductors come in a wide range of sizes, from the IHLP 1212, which is 3mm by 3mm, up to the IHLP 8787, which is 22mm by 22mm, and are available in various heights as well. They feature a powdered iron construction, which provides a soft saturation, which I'll talk about in more detail in a few minutes. The low-profile package and wide terminations provide excellent mechanical shock and vibration performance, especially in engine-mounted applications. The IHLP inductors also exhibit very impressive current ratings. For example, a 1 microhenry IHLP 8787 is rated for continuous operation of 69 amps, which is defined as the DC current that will cause an approximate increase in temperature of 40 degrees C. These inductors can also be operated up to 180 degrees C, which I'll also talk about more in a few minutes. The IHLP technology was originally created and patented by Vishay and features a very unique construction. The high-temperature copper magnet wire is wound first, and then ultrasonically welded to a copper lead frame that is plated with nickel and tin. Then a proprietary blend of low-loss iron powder is pressed around the winding and lead frame at a very high pressure, and the resulting assembly is cured at a specific temperature, which results in a very compact inductor. There is no wasted space since an air gap or bobbin is not required, as you might find in the construction of a typical inductor. The copper wire and lead frame carry current, and the powdered iron carries flux, which results in the most efficient inductor possible in terms of the volumetric density. In addition, since the winding is completely contained within the magnetic material, you effectively get a magnetically shielded inductor, without having to add a separate shield as you might find in other inductors. Also, due to this composite construction, these inductors exhibit ultra-low buzz noise. In terms of the saturation characteristics of the IHLP compared to a standard ferrite inductor, there's a drastic difference in performance. The red curve illustrates a typical ferrite inductor as the current is increased for a given inductance value. The curve is very flat up to a certain current level, known as the saturation point, at which there is a significant drop in the inductance. As the current continues to increase, the inductance continues to drop until the inductor behaves more like a resistor, which is obviously not the desired result in most power supply or filter designs. In contrast, the blue curve illustrates the typical performance of an IHLP inductor. As the current is increased for a given value, the inductance decreases very slowly at a nearly linear rate, but never reaches a hard saturation point like the ferrite. This is a significant advantage in performance, knowing that your inductor will continue to behave like inductor over the entire range of current. It also allows the power supply or filter to handle high transient current spikes without saturation, which improves the ruggedness and reliability of the system. It should also be noted that even though the powdered iron IHLPs do not hard saturate, we still define a saturation current rating on all of our data sheets. Since the inductance does decrease to some extent as the current increases, we define saturation as the DC current that will cause the inductance to drop to approximately 20% of its initial value. We also provide the inductance versus current graphs for each value on all of our data sheets. Furthermore, a ferrite inductor is very sensitive to the temperature. As the operating temperature increased, that same red curve will shift to the left and continue to do so as long as the temperature keeps increasing. The result is an even lower current saturation point, which typically results in a larger, more expensive inductor to prevent saturation at the worst case conditions. The IHLP inductors, on the other hand, do not exhibit any temperature influence whatsoever with regard to saturation. That same blue curve for a given inductance value will look the same whether the inductor is being operated at -40 C, room temperature, or at the maximum operating temperature. Again, a huge advantage when designing a power supply or a filter. One more benefit of the IHLP family of inductors is the material options that are available. When this technology was first created and released for production, there were only two material choices available, both topping out at 125 C with regard to the maximum continuous operating temperature. The -A1 material was optimized for very high frequency operation, up to at least 2 MHz, so it exhibits the best saturation performance and lowest AC core losses possible. The -1A material, on the other hand, was optimized for the lowest possible DC resistance. It still has good frequency characteristics, up to at least 2 MHz, and the AC core losses and saturation performance are still reasonable. In the years since the inception of the IHLP, there has been continuous improvement in the iron powder technology in terms of temperature and frequency response. There are now two more options with regard to the maximum continuous operating temperature. The -5A material can be used up to 155 C, and the -8A material can be used up to 180 C. Both of these materials have been optimized in terms of the core losses and DC resistance, so the resulting frequency response and DC losses are a good compromise between the -A1 and the -1A materials. There are now also two more options with regard to minimizing the AC core losses as well. The -AH material can be used for the lowest core losses at high frequency, and the -AP material can be used for the lowest core losses under high ripple conditions. There is another relatively new product that is worth mentioning, as it is being quickly adopted by many of our key automotive customers. The Vishay IHLE is our standard IHLP with the 155 C material that's been outfitted with an integrated Faraday shield to contain the radiated electric field emissions. If you remember back to the construction of the IHLP, the winding is completely contained within the magnetic material, so you effectively get a magnetic shield for free. However, this construction does not contain the electric field, nor does any other type of inductor for that matter, since that's the function of a capacitor. Therefore, during radiated emissions testing for EMC compliance, the inductor tends to be the chief offender in many cases when the test limits are exceeded. There are several potential remedies which include an external shield over the inductor or the entire power supply, using an appropriate enclosure as a shield, or trying a new printed circuit board layout. All of these methods can add significant cost, complexity, and time depending on the severity of the problem. In contrast, using an IHLE from the beginning of the design, or swapping out an IHLP if the printed circuit board has already been laid out with the 2 additional terminals for the shield, can be a quick and very cost-effective solution. The results will vary from one design to another, but reductions up to 20 dB in the radiated electric field, when measured at a distance of 1 centimeter above the center of the device, have been achieved. The IHLE is currently released in the 2020, 25-25, 32-32, 40-40, and 50-50 sizes. In terms of the user interface for this reference design, the eFuse can be enabled or disabled using either the on-off push buttons on the board or by an external controller, which I'll describe further in the next slide. The current limit is manually adjustable within a range of approximately 0 to 100 amps, either with the 2 potentiometers on the board or with the external controller. One pot is used for very low current applications in the range of 0 to 9 amps, and the other for higher current applications in the range of 10 to 100 amps. The status of the system is displayed using 7 LEDs on the board. As soon as the eFuse is supplied with power, the ready LED indicates the unit is in a standby condition, and when the unit is energized, the fuse on LED illuminates. The remainder of the LEDs indicate the various fault modes, which can also be displayed in the external controller. To use the web interface, an external controller, which was also developed by Vishay and shown in these pictures, must be connected to the eFuse along with the external power supply I described a few minutes ago. Then a standard LAN cable is used to make the connection between the external controller and a computer. The web interface is divided into 3 sections. In the left column, the eFuse can be switched on and off, errors can be acknowledged and reset, and the maximum current can be set. In the middle column, the currently measured values of the eFuse are displayed: the input voltage, output voltage, load current, and ambient temperature. The right column displays the same status indicators as the LEDs on the PCB. To test the thermal performance of the eFuse with only the attached heatsink for passive cooling, various load currents were applied until a steady state condition was reached, and then these images were captured using a thermal imaging camera. The maximum baseline temperature on the board, with only the control circuitry active and 0 load current, was approximately 25 degrees C. With a 50 amp load current, the maximum board temperature reached approximately 33 degrees C at steady state. And finally, with the full load current of 100 amps, the maximum board temperature never exceeded 80 degrees C during continuous operation. Therefore, the change in temperature between a no-load condition and full load was approximately 55 degrees C with just the passive cooling. Therefore, operation in a vehicle under ambient temperature conditions up to 100 degrees C could be easily achieved with plenty of headroom for the power MOSFET maximum junction temperature rating. If higher ambient temperature conditions are required, the thermal design could be easily improved with some type of active cooling or a different heat sinking configuration. In summary, a high voltage resettable eFuse has been developed by Vishay for the safe operation of currents up to 100 amps at a maximum voltage of 400 volts using a variety of key Vishay components for the implementation. Various safety measures have been incorporated into the design to ensure that the user is always protected from the high voltage, even during overvoltage or fault conditions, and that the power source is protected from either overcurrent or short circuit conditions. Please note that this complete reference design, that is the schematic, bill of materials, Gerber files for the PCB layout, and operation instructions will be available on the Vishay website very soon. Okay, this concludes the presentation. Thank you for your time today. I hope it was informative and relevant to your applications. And please keep Vishay in mind for any discrete component solutions in your new designs.
Thank you very much, Scott. This is Jason here. Can you hear me all right?
I can. Can you hear me okay?
Yes, sir. We're good to go. Thank you for that great presentation. And I know we've gotten a good start to our questions here. Everyone who's in attendance, if you have anything that's come to mind during the presentation, now is a great time to submit those questions for this Q&A. And Scott, I'm excited to dig into some of these with you. The first question that I'm seeing here is about availability. Is the board available? Is there an orderable part number that our audience could know about?
Unfortunately, right now you can't order the complete board assembly. That's something we've talked about, and hopefully that will be available sometime. But right now, as I mentioned in the presentation, you can get all the design materials. So you can get the schematic, the bill of materials, the Gerber files for the layout, and you could, basically create the design yourself. So hopefully someday, but not right now.
Great, thank you. Another question that I'm seeing, Scott, I'll just read out this question here. Our customer uses PTCs for pre-charging normally, but the PTC response speed and holding current is worse than an eFuse. Do you have any suggestions about how to balance that design? Mostly eFuse current set point uses mirror current sources to set, so accuracy is a question there as well. But could you speak to that, balancing the design maybe between PTCs and eFuses?
Yeah, that's actually a really good question, or a couple questions. So I guess the first part, yes, I do see PTCs being used for pre-charge in high voltage applications, but like you said, response time is usually not very critical. So if you've got a few seconds or maybe even up to a minute to do pre-charge, then that's a good way to do it. But we're trying to make that pre-charge seamless to the user. So that's why we've implemented the MOSFET and the resistor, so we can do pre-charge in a couple hundred milliseconds, and you really don't even notice that it's happening. And then the second part of your question, so yeah, there are different ways to make your set points for the overcurrent protection. And yeah, you're right also that some of them aren't very accurate. So we tried to pick a very accurate measurement or hardware design so that typically you can be under 1% as far as the accuracy. So we use those comparators that I talked about, and a precision set point that's set by those thin film resistors that aren't going to change very much at all over time with temperature. So hopefully that will be a very accurate measurement system. But again, there's other ways to do it. We tried to pick what we thought was best. So thanks. That's a really good couple of questions there.
Great, thank you, Scott. Another question that I'm seeing here. Can the current measurements range be scaled according to a user's applications? This person is looking for 125 to 150 amps in particular.
Yes, another good question. So in this particular case, we designed up to 100 amps. So if you wanted to go higher, then yeah, you're going to need to probably add a couple more MOSFETs in parallel, just because you're adding that extra current. And yes, you would need to modify the set points, but again, that's not very hard to do, but it is going to require a little bit of design change. Thanks for that question.
Absolutely. Another question here, maybe talking about how do we work with the design. Do you need to use silicon carbide MOSFETs in this design?
So I guess the short answer to that is no. I mean, this isn't obviously a high frequency switching application, so there's really not any concern about the switching losses. But we are concerned with the overall efficiency and the heat loss. So we did decide to use silicon carbide in this case. But if you wanted to trade some of those, trade some of that efficiency and losses for lower cost, you could just use standard silicon MOSFETs.
Great, thank you, Scott. Another question, can the same design be used for an 800 volt application?
Yes, and again, you'd have to make some changes to some of the components. So you'd need higher voltage MOSFETs, whether those were silicon carbide or just standard MOSFETs. You'd have to change the transient voltage suppressors, and you need to change some of the resistors for the feedback, but that's not really a big deal. But other than that, it would be pretty similar. And in fact, we are in the process of releasing an 800 volt design that's similar to this one. And so you should see that, complete design on our website pretty soon as well.
Another question that just came through is there any testing for radiation tolerance here?
We really haven't done any EMC testing on this design since it's a reference design, so we really weren't too concerned about it. But obviously, when you do your own design, you're going to have a completely different layout because it's going to be part of a bigger system. So, yes, for sure, you'd want to do that, that type of testing, and maybe you're going to have to make some modifications. But something we haven't done, maybe we'll just do that to, for our own reference. But no, we haven't done that yet.
What about reference design materials? That's a question I'm seeing coming in, Scott. Will the reference design materials be made available for the external controller as well here?
Yes, and I probably should have mentioned that in the presentation. So yes, we want to make that information available as well on our website. So again, that's going to be the schematic, the bill of materials, the Gerber files, and just, I guess, for reference, that external controller can be used on any of the reference designs that we have on our website, and hopefully you've come across those, but we'll be adding more and more of those as we head into later this year. And that external controller that I talked about with the web browser, that will work with any of them. So stay tuned. Hopefully you'll see that soon on our website as well.
And I think, I know we've talked about this already, Scott, but I do see a couple more people talking here in the comments specifically about supply chain and just getting your hands on parts, right? Over the last couple of years, a lot of people have been impacted by the supply shortages. So I know we talked about the availability of the parts in general, but is there anything about the outlook for this moving forward into the next couple of years, or how people will be able to eventually get their hands on these parts?
Yeah, so I'm probably the wrong person to ask about that. I do get that question a lot, and I'm more on the technical side. But yeah, there's obviously still issues in the market, not just with Vishay, but with just about anybody that provides electronics. So things are getting better. There's still some components that are difficult to get, but we're hoping that eases up later this year, early next year. But again, it seems to be just about everybody in the industry. So hopefully we'll get out of this and get back to making more cars and doing new designs. So I hope that answered your question, or at least part of it.
Yes, thank you, Scott. And what I'll remind everyone here who's in attendance, what you'll see on your screen is Scott's email. And I know that he'll be happy to get you connected with the right person if you have specific questions about supply availability as well. Definitely make sure to reach out to him. Next question that I'm seeing here, and I can actually answer this one, Scott. One question is if people can get their hands on this presentation afterwards, and I can confirm that we will be able to distribute that after this session. So for everyone here in attendance, be able to get you a version of the PDF that we just saw Scott go through earlier in this hour. And with that, Scott, I'm not seeing any more questions coming in. Is there anything else that you want to make sure that we're touching on, or anything you'd like to re-emphasize as we're closing out the session here?
I don't think so. Again, thanks for everybody's time this morning, and I think my email's still up on the screen there. So yeah, if people have questions they think of later, feel free to shoot me an email, and I'll try to help you out or answer it, whatever I can do. So again, thank you, and appreciate everybody's time this morning.
Great. Thank you very much to Scott Blackburn and Vishay for joining us for this session here. And thank you to everyone who was in attendance. That was a great Q&A and a very good turnout for what I think was a fantastic presentation. I've been Jason Montgomery with EE Tech Media and allaboutcircuits.com. If you're looking for other Vishay webinars that have been done, you can find that on the webinar section of our website on All About Circuits. I want to thank everyone for taking their time to join this session here today. In the meantime, stay safe, and we'll look forward to seeing you at another live session again sometime soon.